Hello everyone, welcome to the lecture 14 of the course Diffusion in Solids. Today we are going to take an interesting concept which is called the concept of random walk, which is quite unique of diffusion understanding, and we will also see an important equation which is the Einstein Smoluchowski equation and the concept of the correlation factor. The details of further correlation factors will take later, and here are some of the keywords that are for this lecture. So, when we talk about the concept of random walk, did you ever wonder so far that we talk about the diffusion as a representation, or diffusion defines as the atomic movement, but that movement is not having the unit of, or the coefficient is not having a unit of meter per second, but it is meter square per second. Why is that so? I don't know whether it make you wonder anytime, but we will try to see if we can find an answer to that today. And also, you consider this just data. For example, the diffusion coefficient of carbon in gamma iron, which has the FCC structure, is of the order of 10 power minus 10 meters square per second at 1100 degree centigrade. Now, the jump distance, that means an atom is making one jump from one side to another side, and that distance is order of the lattice parameter, which is, let's say, 10 power minus 10 meters. And how many times a carbon is jumping in a lattice? It is in 1 second, it is 10 power 10. Quite an astronomical number, right? Difficult to imagine, but it is true. Very close to the reality that in 1 second it jumps about 10 power 10 times. So now, if I want to calculate, and for the sake of explanation, let us say that a carbon atom is jumping in a straight line and always goes forward. What would it mean? That the total jump distance after 1 hour, that is 3600 seconds, can be calculated as just simply multiplying these quantities into the time, which is 3.6 kilometers, which is abnormally high. Your sample itself is in few centimeters or millimeters at best, right? So, we also know that typical diffusion length are basically in terms of microns, or even in carburization we saw it is few millimeters. Then how do we understand this? So what it immediately tells us, and perhaps a little bit you also guess, is that the motion of the atom is not linear. Okay, it is what we know as the random. So the atomic motion follows what we call as random walk. What random walk means is that it will not just go in a linear motion. It will go random here and there. Okay. So now the challenge was that how do we have a mathematical framework to understand something which is moving randomly. So if something is moving in a straight line, like we calculated just now, you can say, okay, how many number of steps into the step distance, how much time taken, and so on, you can easily multiply. But when an atom is or when a particle is jumping randomly, how do we develop a mathematical framework to understand that motion? So this let us try to understand. So what people try to use is what is known as the root mean square displacement. This you may have got some exposure to this quantity if you remember the kinetic theory of gases, but nonetheless, let us look at. So suppose there is a particle at this point O, which makes jumps in random direction. So let's say from O to A, and we define this vector as R1. So this is the displacement vector, which is R1 from O to A. And then it makes a jump to another arbitrary direction to a point B, where the jump vector is R2, R3, R4, and so on. So after making n jumps, after making n number of jumps, it reaches a point F. So the resultant vector, which is OF, which is equal to r vector, will be equal to the vector sum of all these r1 plus r2 plus r3 up to rn. Okay. So this can be also represented as summation of ri vectors from I equal to 1 to n. Okay, I is an integer here. Now, if there are n atoms, so remember that whenever we are talking about any materials, we are talking about multitudes of atoms. Avogadro number itself has 10 power 23. So you can imagine how many atoms we are talking about. So if all these atoms make a jump in all different directions, the average of r bar, because it is moving forward, it is moving backward, and so on. So the average of all the jumps comes out to be 0. So the average of r for n number of particles comes out to be 0. That is why the atomic movement qualifies as a random motion. But the problem is that if this comes out to be 0, then how do we quantify, or how do we relate this atomic jump to any other quantity? Let's say, for example, diffusion coefficient, because r bar is 0. So then what we try to do, that instead of calculating r which is average, let us try to consider r square, the average of r square, which is the mean square displacement. So therefore, what people try to calculate is average of Rn square, which is the average of square of net displacement of all the atoms. So this, if we now try to see how do we calculate. So for example, for one particle which has undergone n jumps, we can write r vector is equal to summation of ri. So r square is nothing but r dot r, and that can be written as r square is equal to this r is nothing but r1 plus r2 plus r3 up to rn. Now if we start taking the dot product, what you will have is various terms, like let's say from r1, if you start, you will have r1 dot r1, r1 dot r2, r1 dot r3 up to r dot rn. Remember, till now we have made no assumptions. It's just the random motion of here first one particle. So here then you have r2 dot r1, r2 dot r2, and so on. Now if you see carefully, in each bracket you have this term r1 square, r2 square, similarly you have r3 square up to rn square. Plus you will have also terms like r1 dot r2, r2 dot r1. So which can be written as 2 times of r1 dot r2. Similarly, plus 2 times of r1 dot r3 up to r1 dot rn. And so on, you will have brackets for various terms. You will then have 2 times r2 dot r3 and so on. So then if we write this in terms of summations, what we can write as r square is equal to summation of ri square, I equal to 1 to n, plus 2 times of r1 dot rj, where j varies from 2 to n since r1 is there, plus 2 times of r2 dot rj, where j varies from 3 to n, and so on. To even make it more concise, we can use double summation and write r square as I equal to 1 to n ri square plus 2 times summation I equal to 1 to n minus 1. Another summation j is equal to I plus 1 to n ri dot rj. I hope it is clear. And then if let's say theta ij is the angle between ith and jth jump vectors, okay, then we know that dot products between two vectors is nothing but their magnitudes multiplied by the cos of angle between them. So if theta ij is angle between ith and jth jump vectors, then r1 dot or ri dot rj is nothing but modulus of ri multiplied by modulus of rj into cos theta ij. And now if we talk about, if we start bringing the fact that we are, let's say, talking about the atoms in the crystalline solids. Now in crystalline solids, its different r vectors are equal, or if we assume that they are almost equal, we can write mod r1 is equal to mod r2 is equal to mod r3 is equal to lambda. These are typically of the order of the lattice parameters. So if you substitute this and this here in this equation, you get r square is equal to n times lambda square plus 2 lambda square double summation cos theta ij. And if I take n lambda square out, then what I get is r square is equal to n lambda square 1 plus 2 by n, because I have taken n also out, so by n double summation cos theta ij. Now, if I take this r square, this was, remember, for only one particle, but if I take it for the n number of particles, that it becomes average of Rn square is equal to n lambda square 1 plus 2 by n, and average of cos theta ij of all the atoms between the ith and jth jump. Now, if there is a true random walk in solids, then the summation or the average of cos theta ij is equal to 0. What it means is that if ith and jth jump factor for one is in one particular direction, if let's say cos theta is 1 by 2 for ith and jth jump factor for one atom, for some other atom it will be minus 1 by 2. So this will cancel out. So the average of cos theta ij for all the atoms comes out to be 0 if the walk is truly random. So which means that the average of Rn square is written as, because cos theta ij is 0, so the average of Rn square is basically n lambda square, and therefore this Rn square becomes root n into lambda. And therefore now if you consider for the case of carbon diffusion, if your n is 10 power 14, lambda is 10 power minus 10, then the root mean square displacement comes out to be 10 power minus 3 meter, which is a millimeter, which is still a more realistic estimate. Okay, so basically what we understand is from this treatment is that when it comes to the random motion of particles, or so to say the random motion of atoms in solids, then the quantity to look at is not the average displacement, but root mean square displacement. So basically you calculate the square average displacement and then take the square root. So the root mean square estimate is the right quantity to look at. Now the question is that, suppose, okay, now I have calculated this root mean square displacement. Now how do I basically relate it to the diffusion coefficient, or how do I apply it to the movement of atoms that takes place during diffusion? Okay, so for that, so as I said, that how do we relate this mean square displacement to the diffusion coefficient? So to do that, what we do is, let us assume a collection of n atoms, capital N atoms, centered at origin at t is equal to 0. This is valid, you consider n particles or you consider n atoms, this is equally valid. This, if you see those who have some inclination for mathematics, there is a beautiful mathematics here. So we assume that a collection of n atoms centered at origin, and in a time interval of t is equal to tau, tau is fairly a small time interval, this collection changes its location and is centered at some point in the coordinate system whose location is x, y, z. So if I represent it graphically, it is that this is the collection of n particles which is centered at this origin 0, 0, 0 at time t equal to 0. And now after a time t is equal to tau, this collection of particles moves and is now centered at a point P, which is x, y, z. So and this resultant vector r, this resultant vector r is written as xi plus xi cap plus yj cap plus zj cap, zk cap. So here basically x, y, z are the projections of r on the coordinate axis. Now how do I proceed further? So to proceed further, Einstein suggested a probability function, which is, see the definition very carefully, uh, which is phi of capital X comma tau, which says this function defines the probability that a particle has increased its x coordinate by capital X in a small interval tau. See, there is a collection of particles here centered at the origin. There is a n number of particles here. Now, one particle may move, may change its x coordinate by this amount. Some particle may change by this amount. Some particle may change about this amount. Now, what Einstein defined as a probability function is, what is the probability that a particle in a time interval tau has increased its x coordinate by capital X. So, this is how the phi of x comma tau is defined. Now, how do we use that probability? So, to use that probability function, this is how we try to picturize. So, at t is equal to 0, suppose as we said there are n particles at origin, and at t equal to tau, the number of particles at any plane x equal to capital X, that means at any plane where the x coordinate is capital X, will be given by capital N times phi of x comma tau. That means I had n particles, okay, and there is a probability that each particle can increase its distance by capital X. So, I take that probability, multiply by the number of particles, that will give me the number of particles at plane x equal to capital X. So, this is pictorially represented here. Now, what this picture tells you, that here it is the c of x comma t plus tau. A tau time before, or t time before, at any plane c of x minus x1 comma tau, there was a certain concentration of these particles. Similarly, at a position of x minus x2, there was certain concentration of the particle which is given by c of x minus x2 comma tau. At a plane which is x minus x3 a distance away, the concentration is c of x minus x3 comma tau. So, at time t equal to tau, this is the concentration, and tau time before, the concentration is given by this. Similarly, a tau time ahead here, this is x minus x4. Don't worry about the signs of x1, x4, x2, x3, etc. So, if the concentration, as I said, at any x equal to capital X and t is c of x comma t, then the concentration at x equal to capital X and t plus tau is given by c of x comma t plus tau is equal to c of x minus x1 into tau into phi x1 comma tau plus c of x minus x2 comma tau dot phi of x2 comma tau. See, let us understand this expression. What it means is, what is this quantity? C of x minus x1 comma tau. This is the concentration of the particle at this plane. When you multiply this by the probability function x1 comma tau, it means what is the probability that the particles located here changed their x coordinate by the amount x1 and hence reached here. Similarly, the particles present here, what is the probability? So, when you multiply it with the probability that the number of particles which changed their x coordinate by x2, this gives you the quantity that how many particles reached from x2 plane to here. So, sum of all such planes will give you the total concentration of x at this position, which is c of x comma t plus tau, which is the summation of all this. And in a summation notation, it can be represented as summation over all capital X, c of x minus x comma tau multiplied by phi of x comma tau for all capital X. Now, if I use the Taylor series expansion, I can write c of x comma t plus tau is equal to c of x comma t plus dou c by dou t into tau plus dou square c by dou t square into tau square by 2. Similarly, I can also write c of x minus capital X comma tau. So now I am taking Taylor series expansion about x. So then I can write c of x comma t minus dou c by dou x into capital X plus dou square c by dou x square into x square by 2 and so on. Now, if I neglect the higher order terms of tau and x, remember that tau and x are smaller quantities. And if I substitute the above expressions in equation 1, so the equation 1 was this here. So I take basically I ignore the higher order terms here and substitute this here. So what I end up getting is c of x comma t plus dou c by dou t into tau, which is what you get, is equal to, so summation of c of x comma t minus dou c by dou x into capital X plus dou square c by dou x square into x square by 2 into phi of x comma tau. Now, let us open this bracket. So what you get is 3 summation terms. First one is summation over all x, c of x comma t plus multiplied by phi of x comma tau minus, now summation over capital X, dou c by dou x into x multiplied by phi of x comma tau. Remember, this is phi here, it will be multiplied to each of the terms, plus summation over capital X, dou square c by dou x square into x square by 2 multiplied by phi of x comma tau. Now, since the summation is over the capital X and c of x comma t doesn't contain capital X, I can take this out. So c of x comma t summation over capital X phi of x comma tau minus dou c by dou x summation over capital X into x times phi of x comma tau. Remember, I can only take dou c by dou x out because it doesn't involve capital X, but this product remains, plus dou square c by dou x square can be taken out, summation over x into x square dot x square by 2 multiplied by phi of x comma tau. Now, what are these different summations? Now, first one is easy to understand. So summation over x phi of x comma tau is 1 because this is the summation of all the probabilities. This means it is the summation that all the particles have changed their distance by x coordinate, by a certain x amount. So that has to equal to 1. So that means that this can go to 1 simply. So you have c of x comma t plus dou c by dou t into tau, which is the LHS, is equal to c of x comma t minus dou c by dou x into this summation here plus dou square c by dou x square summation over x square by 2 into phi of x comma tau. Now, if you basically cancel this c of x comma t, what you get is dou c by dou t into tau is equal to this expression. Let us call this as equation 2. Now, how do we evaluate RHS? So you see, this is the RHS, which involves the summation of x dot phi of x comma tau plus summation of x square by t into phi of x comma tau. So to evaluate this, if you consider n particles, a collection of n particles, then in a time interval, remember, and when I say particles, it can be any, it can be atoms also, any n particles. So this is a general treatment. So in a time interval tau, let's say out of these n particles, n1 have increased their x coordinate by x1, n2 have increased by x2, n3 by x3 and so on. That means I have n particles, all of them have changed their coordinates by some amount. Okay. So let's say n1 of them have increased their coordinates by x1, n2 have increased the coordinates by x2 and so on. Now, if I take average of all these x's, average of all these x, it is nothing but average of this x is equal to n1 x1 plus n2 x2 plus n3 x3 and so on divided by n. So the average of x is equal to n1 x1 plus n2 x2 divided by all the total n. Now, what is n1 by n? n1 by n is nothing but the probability x1 phi of x1 comma tau. Similarly, n2 by n is nothing but probability phi x2 comma tau. See, we define the probability in this way only, that what is the probability, what is phi of x comma tau in a time interval tau, how many what is the probability that the x coordinate has increased by the amount x. So similarly here, when we are talking about n1 by n, it is nothing but phi of x1 comma tau. That means n1 have increased their x coordinate by x1 divided by the total number of particles gives you the probability that the x coordinate increased by x1. Similarly, phi of x2 comma tau. So that means that average of x can be written as phi of x1 comma tau into x1 plus phi of x2 comma tau into x2 plus phi of x3 comma tau into x3 and so on. So here it actually just I'll make this change small. It goes on like this, and therefore the average of x can be written as summation of summation over capital X x dot phi of x comma tau. Similarly, summation of x square can be written as summation of over x x square dot phi of x tau. Now, therefore, substituting this in equation 2, we will get dou c by dou t into tau is equal to minus dou c by dou x average of x plus dou square c by dou x square average of x square by 2. Now, for a true random walk, the average of x will be equal to 0. That means when I say x1, when I say capital X, x1, x2, x3, this can be positive, negative. The x1, x2, x3 can be positive, negative. It depends upon in which direction the atom is moving. And if it is truly random motion, some particle may be jumping forward, some may be jumping backward, and so on. So the average of x is equal to 0. Therefore, what you are left with is dou c by dou t into tau is equal to average of x square by 2 into dou square c by dou x square, which means that dou c by dou t is equal to average of x square by 2 tau into dou square c by dou x square. Now, it is sounding familiar to you, I hope. If you compare it with the fixed second law, which is dou c by dou t equal to d times dou square c by dou x square, what you get is d is equal to average of x square by 2 tau. So, for a cubic lattice, the average of x square, y square and z square are equal and are equal to can be written as average of r square by 3. And if you substitute this back in equation 3, what you get is d is equal to average of r square by 6 tau. This is known as Einstein Smoluchowski relation. So you see here now how this diffusion coefficient we have related to the mean square displacement, average of mean square displacement. So earlier also we saw that this average of r square is equal to n lambda square if the walk is truly random. So if you say that gamma is defined, this is a capital gamma, which is a successful jump frequency, then the number of jumps is equal to the successful jump frequency into the tau, and tau is the time. So the average of r square can be written as tau into t gamma into tau into lambda square, and therefore the d can be written as, so you can substitute average of r square here with gamma into tau into lambda square by 6 tau, and then you get d is equal to 1 by 6 times gamma into lambda square. So this is again an important relation which talks about the diffusion coefficient related to the jump frequency into the square of the jump distance. So now you know that why from this relation, and from here you know why the diffusion coefficient has a a unit of meter square per second, because we are talking about the random motion of particle, which is characterized by the average of mean square displacement, not just the average displacement. So just an activity question for you: will this relation be valid for non-cubic lattice also? If not, how will it change? So please try to figure out the answer for yourself. Now, towards the end of this lecture, I am just going to introduce you the concept of correlation factor. The details we'll be covering in a couple of lectures ahead in this week, in the next week, sorry. So earlier we have seen that average of Rn square. So the Rn square is equal to n lambda square 1 plus 2 by n double summation average cos theta ij. Now, if the walk is truly random, then the average of cos theta ij is 0. But if the walk is not truly random, what is meant by walk is not truly random is, that means there is a certain preference for a particular direction. Okay, so let's say just a simple case that atom has more preference to move in a forward direction. So the number of jumps in the forward direction will be more than in the backward direction. So in that case, the average will not come to 0. So in that case, average of cos theta ij is not equal to 0, and therefore the Rn square average is equal to n lambda square into f. This f is equal to this quantity, which is 1 plus 2 by n double summation cos theta ij, and is called as a correlation factor. It is called as a correlation factor. So the earlier what we saw, the d is equal to r square by 2 tau, is the d which correspond to truly random motion of particles. And if the walk is not truly random, then the d star is equal to f times d random, and this f depends upon the mechanism in consideration and the crystal structure. So just briefly, I'll tell you about the atomic jump. So any movement of atom is characterized by the atomic jump. That means you have the initial state. Let's say an atom is located here in the interstitial site here, and it goes through a transition state where it is between the two atoms. It tries to push the atoms apart, and then it goes to the final state from here to here. This process is, so as I said, the atomic migration is the sequence of result of this localized jumps, and it occurs usually from one side to the nearest neighbor side. So from here to here, let's say in this case. And the jump rate gamma, capital gamma, has Arrhenius time dependent on temperature. So where gamma b is equal to nu naught into exponential minus delta gm by kt. B refers to this atom. So here, if this is A atom, this is a B atom, and nu naught is called the attempt frequency, which is of the order of the Debye frequency. That means how many times basically the atoms try to jump here. And the delta gm is equal to the delta hm minus t delta sm, and the actual value depends upon the mechanism involved. So this is how it can be represented graphically. You can see here that this is g and this is the coordinate here, and if the x coordinate, so if the atom moves from here to here, so it has to push these two atoms apart. So it has to push these two atoms apart, which is characterized by an increase in the free energy of the system. So this is like the activation barrier that it needs to cross to, and then it comes down to this final position. So this barrier that has to be crossed, this is known as delta gm, or the activation energy for migration. So with this, we will end today's lecture, and next class we will talk about the mechanisms, and then a little more details about the correlation factors also. So thank you.